talking to us about a topic which is three-dimensional. So please, Thavisha.
Thank you. It's so nice to be here. And yes, the sister gave us sort of a brief introduction to who I am. And I'll be talking to you about a lot of the work I've been doing during my time at MPIA and mostly at Flatiron and some new stuff that we're very excited about. And I have some absolutely amazing collaborators, so big shout as well. Why it's so important. Very ingrained in everything that's happening in the universe. The life cycle of dust takes part everywhere. Starting from if all stars produce dust. Is there a stick or something, Cisco? Or shall I just sort of?
Maybe you have a pointer on your computer so that
you
can
follow. Ah, there we go.
Oh, that yes. Yeah. Oh, yeah. That also works.
Yeah. So you've got evolved stars, so AGPs, red supergiants that produce the dust, and then it's put out into the interstellar medium by supernovae, planetary nebulae, and the stellar winds. And then there's processing in the ISM itself, and then it's taken back into star and planet formation. So the life cycle of dust is ingrained in everything that's happening in the universe. So without understanding everything that's happening with dust, the processes, the structure, we can't fully understand what's going on within the universe itself. So why is dust such a good tracer? Why do we use it so much? It's because dust has this very unique ability, of course, that we know, which is it absorbs and scatters starlight, so extinction. And what extinction lets us do is this absence of light lets us trace the structure by absorbing this matter. And so one of the problems, though, with extinction and why we're trying to move on from just using extinction is that extinction is an integrated quantity, which I'll sort of explain in a little while. So you lose everything that's behind this wall of dust that you're looking. It's basically compressed down. So we want to sort of move on from using just extinction to trying and expanding it out a bit more. So Gaia revolutionized this field, especially with DR2 and now DR3. What it did was it gave us very precise stellar parallaxes and stellar parameters. So what the stellar parallaxes now let us do is basically map out all our star positions. And from those positions and the extinctions, we can basically say, okay, star here has this amount of light taken out of it, but the star in front of it has less light taken out of it. So with these precise distance, we're able to basically build a three-dimensional extinction map, but go one level further and go from extinction to the density. And the sheer number of stars that we have from Gaia lets us not only probe the large-scale structure that we had from a while back, including with Finkbeiner and Davis, but we can now actually start looking into molecular clouds, start probing into them, start looking at these really fine filamentary structures as well. So this is where we come into dust cartography and doing it in 3D. So like I mentioned, the stellar parameter that we get is extinction, which is AV. But what we really want is the density, which will let us trace the dust structure itself. Because extinction inherently is an integrated quantity, but what we want is the derivative of that so that we can actually see, okay, how much dust is over here rather than how much dust is along my column. So we have these couple of these challenges to deal with when dealing with dust cartography, which is one of it is that what we want is density. But unfortunately, what we have is this extinction parameter. So we have to be able to sort of build up this process that will let us go from a modeled density to our observed extinction. And there's this problem that we refer to as the fingers of God effect in galactic dust cartography, which is very similar to sort of what we see in extragalactic when you put all the galaxies together and you see these structures extending towards us. We see very similar effects when we look top down in the galaxy, which is these stripes. And this is what we call fingers of God effect in the galaxy. And the main reason for this is that even though Gaia gives very good parallaxes, it's still not as good as our on sky values. So because of that, we basically have a better handle on the uncertainties on our L and B than our distances. So when we put it into a model, the model can basically decide, oh, well, I have this amount of this uncertainty range. Maybe I might put the cloud here, or maybe here, or I might expand it out slightly more further. So because of this, we see this striping effect. And you can minimize this, and a lot of work has gone into trying to minimize this, but you will not get rid of it until we have much better parallaxes. So probably looking at Gaia near, which is not for till 2045 or something. And then, of course, you have this other issue that dust density must always be positive because it's a physical quantity. We can't have negative densities. And so related to this is that extinction must always be monotonically non-decreasing. So this means it must always go up or flat, but never down. And then, of course, galactic structures multi-scale and multi-resolution. So we have to capture all this rather than treating everything as a single blob or a single filament. We have to allow all this structure to vary and the model to vary to capture it. Once you try to solve all of this, of course, you run into a lot of computational issues, especially related to memory and runtime. So you have to optimize for everything simultaneously to be able to map the Milky Way out. So this is a lot of my work at MPIA went into doing this, and we came up with this code distribution. And that basically came up with dust distribution, and I'm dyslexic, so I just could not say dust distribution together. So distribution was born. And it's completely open source, so the code is publicly available, and with each new iteration, we make the code publicly available, and all the results and really nice graphics are all available in our website as well. And what it does is it takes in any stellar distance and extinction catalog, and it'll give you your 3D dust densities and extinctions. So in any parameter range, you could basically have a molecular cloud. You could have half a galaxy. It's totally up to you what you want to put in. We use a couple of techniques right now in our public version, which we have with latent variable Gaussian processes, which sort of lets us deal with a couple of the issues that I talked about before. And then variational inference, inducing points, and GPUs, which basically improves our memory and runtime. It's both GPU and CPU compatible, but I would highly recommend using GPUs because it's infinitely faster. And so putting all of this together, the work I'll talk about, we've mapped the Milky Way out to circular parsecs in about 2 weeks, basically, in a cluster at Flatiron. So let's get a handle on some of the terms before we go on to the actual work. So Gaussian processes is extremely well defined with Rasmussen and Williams. So if you ever want to learn anything about Gaussian processes, this is the book to go for. It's really nicely described, but it's basically this infinite set of functions that we can then use our data to narrow down what our functions are and therefore a model function that we want. So it's quite a powerful spatial tool, spatial mapping tool because of this. So you can have any dimensional Gaussian process that you want. And one of its sort of highlighting features and why we really like using it is because it gives you interpretable parameters. So you know what all your parameters are, and they can be tied to a physical parameter with some understanding. And also you can get your uncertainties. So it's not sort of out of a black box. You know what your uncertainties are on your model. And what it basically does is you can sort of think of it as this integration process, and it correlates all spatial points if you want to, or you can limit it depending on your kernel. But this is what makes it such a good tool to make these spatial maps with because of this correlation feature. And then we go on to from a Gaussian process to a latent variable Gaussian process, which is what we use to go from our extinction to density, or sort of in reverse. So what we do is we start off with our model is defined in log10 density space. The log10 is to maintain positivity so that we have the monotonically non-decreasing extinction. And then in density space, so that we can then delog it, integrate it, and then compare it to our observed data. So we build sort of this ladder process that will let us get what we want, which is our model, but also then be able to compare it to our observed data. And then variational inference is it's not just a Gaussian process tool. You can use it quite widely in machine learning. And what it does is it replaces your true posterior with a target posterior that's approximate. So you can optimize this approximate posterior rather than your true posterior, and it sort of best reproduces your true posterior. So this really improves your memory efficiency. And then on top of that, what we have is this thing called a sparse Gaussian process, which we build with inducing points. So instead of using all these red points that we have, we put down points in these black points, which are sort of like, it's up to you to decide where you put them, but you have to be informed about where you put them. And you can allow those positions to vary so your model learns what the best positions are for your inducing points. So we put that in as well, and then combined with variational inference, this is what makes it infinitely faster. Yeah. So what we did with this was, one of the first things that I did was map out the galactic molecular clouds. So everything from the large scale Cygnus cloud, which is a high mass star formation region, and then Carina down there, which is about 2.5 kiloparsecs away. And then so the sun is in the middle. So we have the nearby Perseus, Taurus, and Lupus. And then the galactic center is further out there. And what we see with this is when we made all the 3D structures for these clouds is that they've got a vast range of structures. We've got everything from filaments to blobs to voids and cavities. And we can see these features sort of forming in this 3-dimensional space, which you normally couldn't see when you're looking at it in 2 dimensions. And then another thing that came out of this was when you start deriving parameters for these clouds, especially things like mass or your volumes or your filling factors, what you notice is that there's a big difference between what would happen if you just use your 2D extinction map or your 2D emission map, and then compared to when you have this 3D structure, you define a clear boundary and then get your parameters out. So we used for our input data, so from now, all the work that I'll be talking about for our input data, we use this Foyno et al. 2022 catalog, which actually uses Gaia DR2, not DR3, and 2 mass and Ys. And the reason why we chose this is because it's the only catalog so far that's out there that combines infrared data and does a forward model for stellar parameters. So we choose to use this, and with the fact that it combines all the infrared data, we're able to probe deeper into the star formation regions. So one of the things that I said was we notice this big difference in stellar parameters. So we really see this when it comes to deriving the total mass. So this is the dust and the gas mass, which we use some standard conversion factors to go from dust mass and then into gas mass. The blue dots here are the masses that we get when we basically take this 3D map, define our boundaries very carefully, and then derive the mass. The red dots up here are if we take the same cube, so nothing's changed, we take the same cube, collapse it down to our extinction, and then derive the total mass. So we see these very large differences, and the larger the structure, the bigger the difference is. And this is pretty obvious, I think, when we look at these two like separately, because we're carefully defining everything that we consider a cloud. Whereas with the extinction, we have everything that could have gone, all the background material, all the diffuse material around it, some of the foreground material that we didn't take into account here. So you are overestimating your mass by quite a big amount. So this doesn't mean that what you're getting is wrong with extinctions. It means that you need to be aware that you have extra material in there. So this might then affect some of the measurements like star formation rates that you derive. And a really nice feature that I like talking a lot about, and to make this point, is the velar molecular ridge in 2D and 3D, because this makes a really big difference. So with the velar molecular ridge, we're sort of used to this really nice boxy shape. We have A, B, C, and D. And which is sort of separates molecular cloud structures that come together to form this nice boxy shape. But the story changes completely when we look at it in 3D, because what we have now is vela A, C, and D. What we're missing is vela B entirely. It's nowhere to be found in the region that we've mapped, and this is about a kiloparsec that we've mapped here. So what this shows us, and this was hinted at with some of the gas kinematic data. So if you look at some of the, I think it was some of the DAME data, that shows that it's at a much higher, the velocity kinematics are much higher. So it's supposed to be quite a bit further away. And we can see that very clearly now. It's so much further away from where regular vela is that it can't be taken into account when you're measuring your star formation, your masses, or anything for vela. And so this sort of makes the point of why it's important to look at 3D maps and have this very good understanding of your complete structure before you make any inference from it. And from there, we sort of go on to looking at the structure of the whole Milky Way. So we sort of looked at molecular clouds, and we now go on to looking at, this is a 3 kiloparsec, so it's 2.8 kiloparsecs from the sun, and the sun is in the middle. And this was mapped down to, the sampling resolution is 1 parsec. So I say sampling here very carefully because that's the grid resolution we use for a Gaussian process. Whereas there's a lot of other factors that go into defining your exact resolution scales. For example, things like your Gaussian process scale length. So there's a lot of things that need to be combined. So the sampling resolution is 1 parsec. And what we see with this is very nicely, so if we zoom into the inner 300 parsecs, so again, the sun is in the middle, we mapped basically from 10 out to 2.8, just because we didn't expect anything to be inside the 10 parsec region. But what we see is there is this structure within what we define as a local bubble, so within like 100 parsecs. So it's not a complete void. There is still structure. So this sort of has implications for things like if you're doing exoplanetary research and you want like you assume this completely zero extinction space. It's not really true because we do have structure, we do have material in it that does need to be taken into account. It is very diffuse, of course, and very low extinction, but it is there. And this here is the same map that I showed, but now what we do is we collapse our map down in the Z direction. So we're able to capture all the large scale structure of the of basically all sky large scale structure and look at it top down. And then this is again sort of zoomed into the inner region. So one of my favorite things to talk about when looking at this map are all the voids rather than the real structure that we see, because there are these really large voids, things like this, which is possibly an interarm or spur region, we're not sure, but it's a big void there. And then we have this giant oval cavity and the Gulf of Camelopardalis and a lot of other empty regions around. And so one of the questions that we sort of have here is it that there's so much dust we can't see through it and we're getting no dust there? So that's one of the like systematics that we're trying to deal with now. But a similar thing happens, especially towards the galactic center, because there is so much dust there. We know there's a lot of dust. And we expect these extinctions to be much higher, but they're not because we're not able to capture now because there's too much extinction to capture, basically. And we of course have the little local bubble in the middle here. And then here we have all the known molecular clouds, everything from Cygnus to Vela, which I showed before in 3D. And then some of the clouds, Sagittarius and Scorpius towards the galactic center as well. And so once we had these maps, we had to, so one of the things I wanted to do was compare them to some of the young stars and star formation regions and see how they correlate, or are there any correlations, and how they match up. So in the blue dots, what we have are molecular clouds identified, mapped by Zucker et al. They were identified in the star formation compendium. And then we have some of the lime dots, which are masers from, so these are young YSO masers, and they're confirmed. And then in the green contours, we have OBA stars. And we can see very nicely, especially with the green contours, there's quite a lot of agreement, especially towards the galactic center. Same with the masers, as well as the star-forming clouds. One of the interesting bits is here, which is where we think W1, 2, and 3, actually, and 4 clouds are supposed to be, but we don't pick them up as well. So there's a lot of debate about how far away W1, 2, and 3, and 4 are. So this probably is evidence to say that it is quite a bit further away. But we also have some of the like young stars and OBA stars, as well as some of the masers and clouds here, some of the star-forming clouds here. So we're not very sure as to why we haven't picked it up yet. So that's one of the systematics, again, that we might have to deal with. And then what we can do with dust maps is look into the DIBS correlation. So the diffuse interstellar bands are one of these features that are debated about what it is. We don't have a very good understanding of what they are. There is some research that shows that they might come from the C60 very big molecules. But with DR3, there were 2 studies that was done, one by Sagery 2023 and one by within the DPAC by Schultes 2023. So with the Sagery map, when we compare it to ours and when it's been compared to other 3D dust maps as well, there's no correlation. We don't see any correlation with the dust. But when we compare it with the Schultes data, we see a correlation, and so do the others. So we're not very sure what's going on there. One paper says it's correlated, one says it's not. It's something that's been explored. It could very well be down to, again, systematics with determining the DIBS parameters as well. So I've talked a lot about the 3D dust maps, but one of the things that I really noticed when I was working on this is how, while a lot of the dust maps are very similar structure, they also have a lot of big differences. So here I show a comparison of 3 of the latest dust maps, including the work I've been showing. So we compared them in 2 different ways, and we notice these very large differences in all of them compared to each other. So there are a lot of, especially with these Gaussian process techniques, there are a lot of these systematics that we need better understanding and better handling on. So again, this is not saying one map is wrong or the other one is right. It's saying that when you're using one of these maps, be careful, understand what the systematics are, and take those into account when you're going to use them. Yeah, and this was one of the fun sort of parts of making these dust maps, is all these amazing visualizations we can do with it. So this was made by Thomas Muller at MPIA, so one of my collaborators. So they took the 3D dust data and used Blender, I believe, to make these maps. And this is also available in augmented reality in our website, which is very cool. So you can sort of walk through it. Yeah. So this is what the inner circular parsecs of the Milky Way looks like, at least according to me. Now I'm going to talk about something that's very exciting recently that I've been working with Blakesley Burkhart at Flatiron. So it's quite a nice story, because Blakesley came to me one day and she was like, there's this large structure that I find I can't match to any known molecular cloud. What do you think about it? And I saw this map and I thought it was huge. I was surprised that we hadn't really identified what this is. And I wanted to poke into my dust maps and see if it's really there. Is there some sort of weird artifact? What's going on? And this basically led us to identify what we now call the EOS cloud, based on one of the NASA SMEX missions, which we're proposing, that was first discovered in fluorescent H2. So this is data from Joe et al. 2017. So this data has been public for a very long time. and we just happened to stumble upon it. And it's quite a large cloud as well, but what's quite unique about it when at first glance is that it's quite high up in latitude. So it's not traditionally where we expect clouds to be. And it's very close to us. The sheer size of it meant that it had to be close to us. So that was one of the things I was pretty sure at and why I wanted to go look at our dust maps. And so we're probably looking at about 50, I think this is about 50 parsecs and 35 in width. So we wanted to look at multiple other traces, see what happens. So we looked at the H2 to continuum ratio data from the same study, and it's much better defined here and stands out really nicely. And so we chose to use that as our base contour to sort of define parameters for this cloud. And what makes it cooler is that now we look at the oxygen 6 and we see a big gap there. So it is really there and it's not ionized. So that's what we can see from this data. And this is where it gets really interesting, is that when you look at CO data, so this is the Dame map, but we also look at the Planck, we looked at the Planck maps as well in CO. And we can't see anything there. It's completely void. We have this tiny little CO nugget over here, which has is very close to us based on its kinematics. So you can sort of see based on the kinematic scale. So it's quite close to us. So we think it's associated with the cloud, but we're not 100% sure. But that's the only CO that we have. So we have a CO dark molecular gas cloud here. And it's probably one of the largest CO dark molecular clouds that's been found, if not the largest. We're not very sure about that, so we're digging into that. That's completely void of CO gas. And we looked at a bunch of other traces as well. So in H1, it's diffused. So we know it's molecular gas. And then when we look at this quarter keV soft X-ray, we also see this really nice outline that outlines the shape of the cloud. This also gives us evidence that it's nearby because it's absorbing the background X-ray emission. And then we looked at the Planck data, and here's the column density based on Planck data, and we can see the cloud very nicely again. And we think this is the little CO nugget that we're seeing in dust over there. And I'm not sure how clear these lines are over here, but when you compare the cloud magnetic field ordering to its surroundings, the magnetic field is much more ordered within the cloud than its surroundings. So this gives us evidence that it's a single structure and not multiple structures. But of course, we can confirm all this by looking at 3D dust. So what I did was I looked at my 3D dust maps and looked for this shape, basically. And we can very nicely separate out what the EOS cloud looks like from everything else because there's nothing around it. It's just completely void. And we have the EOS cloud here. I cut out the front part just so I can fit it into a nice scale. But the cloud is about 10 parsecs in width. So it's basically this big flat sheet that we're seeing. And in extinction, so when we take our 3D density cube, collapse it into extinction, we have this shape, which matches very nicely with our Planck extinction. Sorry, this is the Planck dust column density. So yeah, so we can basically, using our 3D dust maps, confirm that the cloud is at about 90 parsecs. So its densest regions are at about 90 parsecs. And then it's at, its physical size is about 10 parsecs along the line of sight, about 53 parsecs, and 35 parsecs in width, assuming it's at 90 parsecs. It could be slightly further away or closer based on other dust maps, which means the size will change slightly, but it will still remain a very massive cloud. And this is the masses that we get for the cloud, the dust mass, and then the total gas total mass, including the gas and the dust. And this is what the cloud looks like in 3D. Again, I cut off the front to make it easier to render, but I really should put the front back in. this sort of brings me to the end of my talk. And I'll leave the summary up and take any questions.
Thanks, nice presentation. Questions?
Yeah, this CO dark. I mean, when the Planck data was released, it was, I mean, the many regions where you have this kind of region where you have the dust emission from Planck, but no counterpart in the CO. But this is probably the closest one, right? Where
Yeah.
you have measured.
Yeah.
Because you have the 3D, which is the typical volume density of this cloud. It's 10 to the 3, 10 to the 2.
Oh, column density. Oh,
The volume density.
volume density. Yeah. Let me just go back. So in density, it's about, we're looking at about 0.08 magnitudes per parsec. Is that no the
Units,
density?
maybe grams per cubic centimeter or something.
Oh.
Particles per cubic centimeter, yeah.
I don't know off the top of my head, but I can make a calculation and get back to you on that.
So that means that the fact that there is no CO is because this is very thin, so the UV radiation is destroying the CO. That's
Probably, yeah. So one of the things we're actually trying to figure out now is, yes, was there CO and was it destroyed, or is it young enough that it's just starting to form CO? We're not very sure about that, actually.
I guess probably because this is quite wide, using quasars in the background and trying to make a spectrum in the millimeter to see if you can see any of the, I don't know, carbon, like a simple molecules, CCH or so.
Oh, that's
Maybe form before CO. That would be nice to see.
yeah.
Okay, any other questions? Okay, I have some questions. So I'm interested about in these maps that you made, this sort of the overall maps out to 2.8 kiloparsecs. So first of all, I would be interested to have a number on, you know, how much solar masses of dust are encompassed in that area, and you know, we can compare it with, for instance, star formation in the same area or dust production in the same area, to look at this picture that you showed in the beginning of the life cycle of dust, right? So how do these numbers compare? Do you know?
I have not made it for the whole map, definitely not. So I've made it for all the little individual star formation regions that I looked at, but not the whole map. But the code exists to do it.
Yeah.
So I can definitely get back to you on that, but not off the top of my head.
Do any arbitrary, maybe like a number that you make a graph starting at the sun, and then going out, and then
like
having sort of cumulative dust mass contained, you know, out to as far as you can go. So that would be an interesting output to have.
Yeah, definitely.
And the other thing is, you also showed a couple of maps where you say, okay, here I'm comparing it with star formation regions. And as you can see, there is no correlation, you said. And I'm staring. It's like, how do you decide there is no correlation? What is sort of, because you are so precise in your sort of your numerical methods, and then you just show us this map and you sort of eyeball, there is no correlation. You must have numerically decided there is no correlation, right? In the positions. I mean, the positions matter and the distance matters, right?
So we basically did a density point correlation. So very simple. It was like, do these density in this region sort of match up to what we see with the cloud density? So the little dots density, basically.
Okay.
So it was very simple assumption. So it could have been done much more rigorously, definitely. So it's very simple. It's a little bit above eyeballing it, but definitely nowhere near as doing some sort of like p correlation or something like that.
Okay.
But with the DIBS, that was very much just eyeballing it, because we don't see, like, it's so all over the place. There's just no like correlation to look at. So we didn't really see any point with that.
It might be good to still try to quantify this kind of statement.
Yeah.
And then the other thing is, again, completing the circle of your life cycle of dust, you're looking at dust consumption in star formation, but you could also look at the dust producers. Know how do they correlate with the dust?
Oh,
maps?
yeah,
So that's another
absolutely.
correlation that would make
Yeah,
sense.
it's
Yeah.
always been one of those things that I talk about that I wanted to do.
In your
Background, I know.
Yeah. Yes.
Yeah, I think so. One of the reasons, I mean, it's like you could probably correct me on this. Like one of the things why I didn't start looking at the older stars basically is because I wasn't sure how good the distances are to them. So would we be able to place them well enough on
Yeah,
a 3D
that
map?
is a problem. Yes. Yeah.
But we could
yeah.
probably get a first order understanding with what we
Yes.
have.
Yes. Yeah.
Yeah.
Okay. Any other? Yeah. Go ahead.
Thanks for the talk. One question about, so when you were comparing the masses that you get directly from the full extinction map with the one that you said, carefully selecting the boundaries of the cloud. So I have two questions here. So what do you mean by carefully selecting the boundaries?
I knew that was coming.
And the other question is, so if you compare the masses of the total extinction with the carefully selected clouds, the difference is a factor of 10.
Yes.
Which then it's, so 90% of the emission would be in this more diffuse gas. And my question was, is this really diffuse gas that it's in between this cloud, or it's because when you are doing the full extinction, could be material that it's in the background very far away? So I mean, you could check it by setting some constraints in the distance, integrating everything, and then carefully and see what is the amount of mass that's in the diffuse gas inside the cloud.
Yeah, so first question, how do we define the boundaries? That was done with Astrodendro. So we put down Astrodendro contours, and then we had, I think it was the parent, which was just above the mean background is what we considered to be the cloud. And so that's how we got the boundary. And the second question of background dust is there is no background dust because what we did was we took a cube. We cut the cube, basically.
So you get full extinction integration is this cutted cube?
Yeah, so if I just go back to that plot, yeah. So basically this map is built by collapsing this cube. Of course, that's the bottom part of it as well.
So it's really within the.
It's really within, exactly, yeah.
90% of the mass is there.
Yeah, exactly. Because bear in mind that there is also, so very deep within, because this is Orion, which is very dense, especially in its cores. So we are not picking up some of the material, definitely. But that is not accounted for in this either. So if you're trying to compare this to another sort of like maybe CO map of Orion, I bet you'd get differences. But this and this, so these 2 points are determined from the same cube.
Yeah, that is possible. Okay. Any other questions? Yes.
Technical question with the, I think you mentioned that the Gaussian process, you use the logarithm of the density, right? So my question is why, I didn't understand why, and also if you are using logarithm, wouldn't that bring issues with having non-symmetric uncertainties?
Yes, we have to assume symmetric uncertainty. So that's one of the issues because Gaussian processes cannot assume non-symmetric uncertainties. So that is a systematic that I was talking about that we need to get a better handle on. And then why we use log 10 density is because if we use just density, it's free to basically go beyond below 0. So we force that positivity constraint by using log 10. But then that then comes into some of the issues with uncertainty again, because you're also not allowing your uncertainty to go down below 0. So that's another systematic with using Gaussian processes.
Any other questions? Okay, if not, let's thank Thavisha again. And I think we're still a little bit early for the pizza, but
Oh,
should be
maybe I should have added more slides.
15 minutes, yes. Anyway, thank you.